response. So the basic reason for this kind of mechanical reason can be easily discussed using the molecular origin of the composition of the ingredients in that material. So what are those molecular origin of mechanical responses or interaction between the species of ingredient of your uh, cosmetic material, or even in our case as aloe vera was our material. So what was the interaction of some additives with this polymeric chain of that aloe vera or the polysaccharides? So this is energetic interaction with the surrounding molecules with and the added particles. So, and the second part is the time scale for which you want to store, means your material need to store that energy. That is also important. And the time scale for which the solid stores energy. So here is the answer. So liquid like material can store energy for a very less time period, time lapse, where a solid can store that energy for a comparatively very high time period. And that's the reason why they are important while designing any new material, new viscoelastic material for this specific applications. So the time accordingly we need to add some additives which will increase its loss modulus, or which will ultimately result in increase of storage modulus. So like if you want to specify that creep or some viscoelastic models to identify that particular viscoelasticity or the creep, how to ascertain that particular model, or how do they behave? So if I draw this line like can you see something on your screen? Yep. And this is your tree. So where your if you provide some stress strain over here, it is constant, and now it is released, stress released. So this kind of material can be considered as what. See, I am showing another situation where the response is at this moment you are starting the stress, and this is behaving like this, and here you are releasing, and now it is decreasing. So this will be your permanent deformation. So this is again the same coordinate and abscissa here, and this third situation where again I am drawing this part where you can easily identify what kind of behavior is it. Like again, at this moment I'm providing the stress, so immediate response, then deformation, then straight line, and then it is again irreversible phenomenon, and then it goes on like this. Now what kind of material will behave like this? You know? So we can say like these are some example of glassy material. So this is represented by glassy systems, glassy system, whereas the material under this curve and this curve. Can you see the screen? I am writing something. I have drawn some graphs on your screen. Are you
Yes,
able to see?
yes, yes.
I have shared the screen. Hello.
Yeah, yeah. It is visible, sir.
Okay, okay. And what is this represented by? So that is mainly leathery substance, isn't it? है And here for this kind of material is mainly rubbery, rubbery material. So this is very simple explanation just to have some basic idea. I am giving you this kind of explanation. Now see what happens. See if you want to model this kind of behavior, how can you model it? Like is it what kind of combination will you use to identify this situation? See, if I further go on drawing some pure liquid, see, it was glassy, leathery, rubbery, and if you go on further increasing it, so what will happen? What will happen? I should draw another one which is represented by some liquid or viscous behavior. है ना? So the viscous behavior I can draw like this is your axis and how should I draw? At this moment, I have initiated that and it is deforming, and yes, it is dissipated. Parallel. This is E, this is tri. So this is the viscous behavior. So accordingly, accordingly, here, if you want to use some model, physical model, how can you draw that for this situation? It is simply for dashpot. Simply that dashpot. Dashpot. Here, if you want to draw a model for this thing, how to draw it? Elastic. Spring only, and here we are having combination of these two, combination of dashpot here and combination of that. So what do you think here? What is the main application, or in which what happens physically? It is deforming, and there is also some permanent deformation over here. Means energy has been dissipated, but it is also affected simultaneously by this Hookean solid kind of phenomena, and that's why we need to use here this combination of this spring viscoelastic solid as well as that viscous liquid. So we need to bother about both the things over here. So this can be for this leathery material. We need to use the combination of these two, that is the spring and the dashpot. Spring and the dashpot in parallel. in parallel. So here we were applying that force, and here is the stretch. So this is for this figure. Now what can you say about this thing? Rubbery material. How can you combine them? See the physical interpretation of this. How does your strain varies with respect to time? So initially, the moment you have provided the deformation, and the same deformation is also more than this thing. So it is a permanent deformation. That's why here is the combination of your series, and it is also showing this straight part over here. This is analogous to this part, and that's why it is the series combination of this thing, what is represented by our simple series connection of this dashpot and spring. है ना? So this is series combination. So this is the rubbery material. Now, if I further explain this chart with some more intrinsic property, how will you identify this? If I apply constant stress, like for certain time period, and I am analyzing that corresponding strain. So this is my time axis. This is time. This is stress. I'm applying stress. So stress is my signal, and this is my response, formation, or the strain rate. So I'm applying constant stress. So accordingly, what do you expect in the case of this behavior? What will be your deformation for an elastic material? It will deform. And in the another situation where I am drawing this part for your zero, that will reverse the value of whenever you increase it, it will increase with respect to time, and at the same time, as you apply this force, initially it will try to become stable, and then it will try to approach that asymptotically, and there will be this kind of gap will be always present over here, what is known as this permanent plastic deformation over here. So that is the thing what we need to apply on this particular things. Now we are having this idea on deformation. So similarly, if you consider this thing for that some polymeric material, and if you keep on increasing the temperature, and if you notice the behavior of that molecules, that its deformation rate. So how can you plot with respect to temperature now? So like if this is your deformation axis and this is your temperature, so this is your temperature and this is your E. It will be Pascal. So see, initially at for the solid materials, if you keep on increasing its temperature, its it will remains at if you keep on increasing the temperature at from this level. So let's say it will initially get its molecule gets deformed and and further increase in this deformation. It will just shift its slope, and then it will go to this rise, and afterwards that glassy temperature will occur, and beyond that further increase in the temperature, then it will again gradually rise. So here it will just melt, just it will just melting temperature of that polymeric material. But what happens between this region, what happens? So that is quite understandable from that easily stretching of that alignment of that material. And here that rubbery state, from this point to this point, there will be some rubbery state, and with this rubbery state within this temperature range, and afterwards again there will be some region which is which is specific to certain type of material, where its temperature will change, and further increase in this temperature will ultimately give melting of that material, and your material get melts. So this way also you can identify your basic phenomena of you can correlate with the creep. Now if we further discuss on similar thing, like what happens to your curve of this strain versus time curve. So how can I draw it? This is your, let's say this is your axis of your E, and this is your time, and this is your E. So the moment you have applied some stress, and thus a deformation will occur, and that's as a result of that deformation, it has increased at this time moment. Now onwards, it will just try to move over here. It will increase its elastic deformation, and then after it will increase in it, and afterwards, when you release the stress, it will this is the realignment of that here there will be some sort of strain hardening will occur, that lower yield limit and higher yield limit, and for ultimately it will also reduce. Now this is recovery, it recovers, and this is your permanent deformation. So here now again, how to specifically use which kind of model fits this particular behavior, how to identify that thing. So how to identify these things? See, these phenomena just now we have discussed. So it is the combination of your spring. If consider all this is one example of a viscoelastic material itself. So for all this phenomena, we need to use that series and parallel combination of that void. So here there will be spring, and here will be the dashpot, but the dashpot is also get compressed, and also it will connect with the one dashpot at the series, because it is going to give you permanent deformation. All the energy is being lost. And for this region, what is the total, how can you represent that model for this region where it is varying in a curved fashion like this. So here also it will be a combination of stretched spring and stretched dashpot, which is in combination with this see here it was the spring, here it was the dashpot, and here again some spring was connected. So this dashpot is stretched over here, and as it is in combination parallel with the spring, so spring will also remain stretched, and that's why it is it is giving you that continuous deformation which is varying with respect to time. But here it is stress relaxed, and that's why now it is relaxing. So that's why this first spring, uh, what was provided over here, so this spring will stretched, it will get compressed over at this position, and remaining these two dashpot and these two dashpot get stretched. So this is how we can easily interpret that model for that spring or dashpot, how to make that combination of appropriate model at a certain situation. So we should consider like why this time dependency, we are considering this time dependency, or how your viscosity or how your loss modulus is associated with the time in all these stress strain characteristics. So for that, again, we need to so it is necessary or advantageous to consider the viscous component of that material of the to identify easy mechanical response. So when a load is applied for a longer period of time or is cyclical, at that time the time dependency is of very much importance. When the load is applied for a longer period of time, or when the load is cyclical, at that time also the time dependency is the predominant factor while discussing the characterizing type material. Like for example, if you consider the effect of body weight on a hydrogel of implanted tissues or any other implant in the spine, so that entire load of that body will be there on that implanted hydrogel, and that's why what will be the its deformation. So for this kind of behavior of implants, which are often made from different type of hydrogels, are require this kind of characteristics. Now when a material must resist failure, like viscous energy dissipation can impart superior mechanical performance. So that's why in that case also, the for example you have the tissue material or adhesive material, which if there is some sort of adhesive material available and which is used for some preventing some failure in the surgical sealing efficiency. So in that kind of material, this property must be required in order to have that easy understanding. So again, the viscoelastic materials exhibit both that viscous and elastic behavior, and the proportionality in the case of that for time dependent, the stress is proportional to the strain rate, where the material specific proportionality constant is known as the viscosity, whereas for elastic material or that elastic nature of that material, the stress is proportional to the strain again, but that material specific proportionality constant is the Young modulus, and that is instantaneous, especially in the case of elastic material, whereas for viscous material, it is time dependent. So TDS in that equation will give us some value of the decrease in the entropy of a material, which is which is responsible to configurational changes that decrease disorder in the system. So see that how does that temperature also plays a role over here, है ना? When you write that equation like sigma dE is equal to du minus TdS, in that situation, another aspect of explaining this stress relaxation, explaining the stress. So again here, let's consider this slide now where when there is some sort of constant stress is maintained over a strain, what will happen? After a longer time period, it will also experience some permanent deformation, and that permanent deformation in the material experiences some initial minimum stress, maximum stresses, and these stresses undergoes a gradual reduction to the equilibrium value. So when does it goes to the gradual reduction in the equilibrium value, that is known as that material is relaxing. So that is stress relaxation of that material. So here in this figure, you can see this material is relaxing. Which material is having more relaxation? This the material denoted by that pink colored bullet is relaxing in more in comparison with this blue or this brown one. So again, the instantaneous stress response is very high here for the pink material, where that intermolecular interaction between the polymeric materials and the added particle was so predominant, and that's why it led to that strain, which was a result of that permanent plastic deformation. And here, in this relaxation, the moment when the stress was released, at that time, the time course and the extent of the stress relaxation is exhibited by, because your material, when you are under the action of high shear, that polymeric chain gets stretched, and as it the polysaccharide chain of the hydrogel or aloe vera gel was stretched, after that time, the interaction of that added particle has caused that all the stretch to realign, and that's why that realignment is the ultimate result of the intermolecular interaction or the interfacial interaction between this surrounding phase and that polymeric chain molecule. So the stress in the material at equilibrium is represented by these things. So here we have represented in terms of strain versus the time. So similarly, what will be stress exerted in that material at this situation? So that stress in this material at equilibrium is representing like nothing is moving in that material. Means once we have flattened this, we have observed this plateau with respect to time for the strain, means no any permanent deformation or no any plastic deformation occur further with respect to time, means there is nothing moving in the material, means no longer it's a time dependent phenomenon. Now onwards, it will become time independent. But for this pink, see, it is gradually decreasing strain. So that's why it is still recovering. So now, depending on your end use, whether your material is going to be utilized as a some body implant, or if it is like some face wash, or like if it is simply a toy, accordingly, we need to adjust its final strain, so that we have to capture we have to arrest that interaction, molecular interaction of the polymeric chain with the additives. And again, this use of additives is very specific in for specific applications. So the uh, so how does that added particle provide that interaction in your final liquid? So for that, again, I'm sharing some drawing. So this is and this is your sigma stress. Now what happens? See, initially as you apply the stress, the deformation, it will start from the origin, and now it's goes up, linear relationship. Now if you find this, what is the area, this is your stress, and so you can find out by noting down, you can find how much energy it has stored at this up to this time. That can be easily find out by using how much by simply using this area under the curve of this triangle, and area under the curve of this triangle, that will give us some idea regarding uh, how much energy has been stored in that material. But now once this linear relationship get over, after some time what will happen? Now the material start yielding, but before yielding there will be some sort of elastic limit will occur. So suppose at this moment the elastic limit occur at this moment, at this point, and just after the on the right hand side there will be, just on the right hand side there will be one point which is represented by upper yield point, है ना? So actually see, in practical situation you can consider this yield point and the elastic limit are same, but theoretically elastic limit means within that limit that material is showing that elasticity. So it is theoretically it is just on the right hand side of elastic limit, but for practical situation that you can consider that are coinciding. Even most of the books also represent, or literature represents, they are coinciding with each other. So upper yield, then there will be lower elastic limit, means within this region there will be realignment of that polymeric chain will happen, and realigned chain again further increase in that stress, that get elongated for further time period, and again it is that chains are stretched now within this region, and once we come here, again now it is secondary deformation plus permanent deformation will occur, and this is the relaxation. Now it is permanently relaxed. So this is general response of more solid like behavior, effects of various stress. So this is what how you can experience that particular behavior of that material over here. So basically that material's response in this region is of very much importance, what occur within this region. So what occur within this region which is encapsulated by this green envelope is of much concern of the type of entanglement in that polymeric material. But at the same time, what is the total entanglement, that is also a characteristic which is represented by this phenomena, and how that patchy polymers or entangled polymers will realign in order to shift that, in order to avoid that entanglement. That is the main characteristics which we can observe depending on this region. So so this phenomena is the characteristics of certain material, as well as this particular region where your material is behaving, showing that stretching of that in realigned polymeric molecules. Now this is simply the chain structure is get released here, that molecular orientation also get changed, and here afterwards that complete deformation that's shown by that solid material. So here, if you take the area under curve for the solid, that tough material, like you can also identify the material like which are tough material, which are soft material, which are soft and tough material, and which are strong and soft materials. So this is how we can identify the characteristics of the material comparative, or we can also make some comparison of that material for our concern. Our concern means depending on that application, what is the actual requirement for of property for our application. Based on that, we need to use our own material, and accordingly we need to design material. So basically this kind of application is used, or this kind of experiments are useful when we are designing some new material for specific use. So in all these cases, this designing of the material using some specific application is important, where
Sir, sorry to disturb you, but we are not able to see your PPTs.
so these kind of experiments what we discussed right now are of very much importance, especially when we are designing new material. So when we are designing new material, we should bother about what is the main property we are bothered about. Means what is the end application of our material. If that material is going to be used as an implant in some human being or some animals, so or like artificial bone, or is it the material which is going to be utilized just as a packing material for the padding. Accordingly, its stress relaxation or the creep behavior need to be modified. Now, as we have seen in our experiments of that polysaccharide network, how do they interact with that additives? So again, that interaction of the material, with polymeric chain network will also ultimately result on its response under the action of particular type of stresses. So that's why if we know the application of our material, accordingly we need to tune its property based on the rheological property requirement based on that application. So accordingly we need to add certain type of additive. Now what kind of additives are useful for certain application, that also matters a lot when we discuss the tuning of the property or the design of novel materials. So basically under the action of low shear, if you want that high storage modulus, in that case we need to add the material which are having more attractive interaction with that polymeric network, and at the same time when we provide higher shear rate, higher strain percent, at that time that must allow easy realignment of the polymeric chain. So at that time their interaction must decrease. So some biological materials, some natural materials, some nanoparticles can be modified accordingly, or they can be doped with some elements in order to offer this property. But again, depending on the surroundings, depending on the polymeric chain and their surrounding, what will be the extent of the attractive interaction and that repulsive interaction, that the competition between the attractive forces and repulsive forces will ultimately decide that ultimate stretching of that molecules. So that's why the ultimate permanent deformation or the plastic deformation of that material depends on the intermolecular interaction between this species present in the gel material. So I have taken some material for this presentation, and this is my research group. My students are working, some are working on some microfluidics. Few students have passed their postgraduate and doing some doctoral work at NCL Pune. He's on his, he has just finished his PhD, and they are doing microfluidics and this. So here I stop. So thank you very much for listening me. So if you have any doubt or any question, I'm here. I'll try to address your question.
Sir, can I ask one question?
Yeah.
Yes. Yes, sure.
Sir, you have drawn you have shown some graphs here, stress versus strain. No
Yes,
doubt
yes.
that we can draw it because the same technical problem I have faced while going on some experiments in my lab. So though we are trying to plot it on the Excel sheet, but still it is not giving a good quality. So some specific software is there to draw such a type of the stress strain relationship or any type of the rheological graph.
So if you are doing rheological experiment using your rheometer, that your TA instrument or Anton par is along with that Rheo Plus or
No, we do not have any software related to instrument which is connected to the instrument, because whatever we are having Brookfield viscometer, but that we have to do note down all the readings manually. So we don't have any connection with any computer system or any software.
I got. So you are noting down your reading manually, then you are need to plot that graph.
Yes.
So origin, ORIGIN. So that is also providing very good compatibility for drawing this rheological graphs. Origin. Yes.
Okay.
Yes, we are also using that.
Okay. So we can just enter our readings there and we will get a plot.
Yes.
Hello?
Yes.
Okay, sir. Yes. Okay, sir. Thank you, sir.
Welcome.
So, any other question? So we have invited our BTech students also for this lecture. From BTech students, do you have any question? Chemical technology for delivering two fantastic lecture in this faculty development program on fundamentals of polymer rheology and soft matter. Thank you very much, sir, and expecting same assistance in the future also.
Okay, thank you very much, Professor Tushar Deshpandeji, for inviting me and for giving this opportunity to deliver this lecture. So thank you once again to your team also, Hannah, who are organizing this event of FDP Faculty Development Program. Thank you very much.
See you soon.